Hello everyone, and welcome to my virtual SAS Global Forum 2021 presentation. My presentation is titled, Do I Have Enough? A macro for sample size determination in simple binary logistic regression and multiple binary logistic regression models. So a little bit about myself. My name is Carl Wilson. I am currently pursuing my master's degree in biostatistics from Grand Valley State University, and I'm also a biostatistics intern at Spectrum Health Office of Research and Education, located out of Grand Rapids, Michigan. So here's the agenda for what we're going to cover for you today. We're going to start by touching base on some background regarding binary logistic regression. Then we're going to cover the sample size determination dilemmas surrounding it, a remedy of these sample size determination issues, demonstration of my macro code, and implications and importance surrounding it. So to begin, binary logistic regression is a type of regression analysis for modeling a binary response. So this could be something like yes or no, dead or alive, has a condition or doesn't have a condition, stuff like that. We see it used in many different scientific backgrounds. You can see this used in ecology, you can see it used in psychology, we can see it used in biology, stuff like that. And despite all this use and application of it, there's no universal convention for sample size determination for a binary logistic regression model. And this can lead to issues of type 2 error, and that you might fail to detect treatment effects, even if some exist, if your sample size is too small. Or you might overspend resources like time and labor and research costs to try and get a really big, gratuitous sample size that you might not need. So here's some more information surrounding the dilemmas. There's an egregious amount of disagreement on what the best method of determining sample size is for logistic regression models. One suggested method is the events per variable method. This is a magic number method, where you specify a minimum number of subjects per explanatory variable. But even this has a lot of disagreement on what the ideal EBV value should be. The general convention has been 10. Others suggest that it should be at least 20, and even others argue that it should be 50 or more. There's also speculation regarding if the EBV method is even valid, as it doesn't consider effect size, significance, or power in its calculation. So to remedy some of these issues, we can look at Hsieh's method. It's a formulaic approach derived from a two-sample framework. You can follow that link there. I have it referenced at the end of this presentation if you want to see the derivation and mathematical proof of this formula. And the formula can also be further improved by multiplying by a correction factor for small response probability. That's also linked. You can check that out if you're interested. And this formula is nice that it actually considers significance level, power, and effect size in the calculation. And the effect size in this case is the log odds ratio of the probability of the response at one standard deviation above the mean of a continuous predictor x. And that's going to be compared relative to the probability of the response at the mean of that variable x. It's also good that this formula can generalize to the multiple binary logistic regression case. So it's good for more than just one continuous variable. You could do it for a model that has multiple continuous predictors. Now that's done by inflating the simple logistic sample size by multiplying by a factor of 1 over 1 minus r squared. And r squared in this case is going to be the proportion of variance explained by x1, which is the original predictor in the univariable model, explained by the regression with the new predictors and the multiple variable model. And this macro is going to automatically do that for you. You just have to choose your variable of interest, and you can plug in the rest of the variables as well. It'll run the regression, it'll get the r squared, and it'll plug all this into a formula for you. So the macro code itself, as aforementioned, it's derived from Hsieh's formula, as well as Whitmore's correction. It can determine the sample size for both simple and multiple binary logistic regression models, and the process is completely automated and streamlined. The macro itself takes several parameters, one being the data set, which is the name of the data set, the response, which is going to be your binary outcome variable, x, which will be a singular continuous predictor variable for the simple model, or if you're doing the multiple variable model, it will be the main predictor of interest. Other x, which is the other continuous predictors if you're doing the multiple model. If you wanted to just do the simple model, you have to set it equal to 0. Alpha, which is the specified significance threshold, and beta, which is the beta level to calculate power. So we can actually demonstrate how to use this macro if we use the example heart data set from the SAS help library. That way all of you can replicate this if you're interested. So what we're going to do is we're going to predict status. It's a variable that has the factor categories dead or alive. And we're going to kind of predict it based on several continuous predictors, or just one predictor to start for the simple case. So what I've done rather than using the whole data set is I've taken a random sample of it using proc survey select. This will be more realistic for how people will be using this macro. So I'm taking a sample size of 100, it's a bunch of random observations, and we're going to try and figure out the necessary sample size for this model to be appropriate. So if we say we're mainly interested in the effect of systolic blood pressure on status, if we use a significance level of 0.05 and a power of 0.8, the macro code is going to look like this. So keep in mind we're looking at the simple case here, so we don't have any other x's. It's going to be just 0, and we're using just systolic blood pressure. And our beta is going to be 0.2 because we want a power of 0.8, and that's going to be calculated from 1 minus 0.8 is 0.2, so that's where that came from. So what the macro is going to output, it's going to output your significance and your beta. It's going to give you the upper quantiles of these two. And it's going to give you the probability of the response at the mean level of x. And it's going to give you the probability of the response 1 standard deviation above the mean of x. The effect size is the overall log odds between these two. In this case, that's actually quite a big log odds ratio. It's a good effect size. So our sample size is going to be small because of that. This also outputs the correction factor from Whitmore, as well as the estimated sample size for the simple case. So let's say we wanted to build a multiple binary logistic regression model. So we want to look at more variables. So if we wanted to include the effect of systolic blood pressure, diastolic blood pressure, weight, height, and cholesterol on predicting status. If we use the same alpha and power, our code is going to look like this. So now other x is not equal to 0. We're including the other predictors. And it's going to output all the same stuff, except this time it's going to give us the regular sample size for the simple case, as well as the estimated sample size for having multiple predictors. So implications and importance. If we wanted to compare this to using the other method, like the EBV magic number method, even if we used a moderate EBV value, so we did like 20 instead of 10, this would give us a sample size of 100 if we're using these 5 variables to predict. So if we fit a model with 100 observations with Logistic, we can see how badly this model performs with this sample size. So once again, I'm taking a sample size of 100 because that's what our EBV value would specify our sample size should be. I'm using a different seed than before in case you want to replicate this. And then I'm fitting in a logistic regression model based off of Logistic. So you can see that all the global tests here, they're all insignificant. And then for parameters, the only one that is significant is going to be our intercept. So this model isn't fitting very well based off of 100 observations. And that's what the sample size you would get from using an EBV value of 20. So now if we fit a model with the sample size that we got from the macro, which was 1,206 if we look back. There it is here. We're going to round up since we're considering it to be humans. So if we go ahead and take a sample size of that value instead and build the same model, if we look, now all of our global tests are significant and only 2 of our parameter estimates are insignificant. So this model runs substantially better compared to the one that the EBV value would suggest sample-wise. So to further touch base on why this is important and how it would be used, I mean, having a proper sample size is imperative for conducting research. So you can avoid failing to detect treatment effects if some exist. And it also helps to circumvent expending way too much time and resource on obtaining a really big gratuitous or overzealous sample size. This macro is more cogent and valid than magic number methods, as we kind of saw, because it's taking into consideration effect size, significance, and power into the calculation, rather than just multiplying how many predictors you have by some magic number. It's also novel in that it automates and streamlines the process, so you don't have to do any of these calculations yourself, and it can be applied to both simple and multiple binary logistic regression, as we saw. And where this will be most useful is for researchers that are doing retrospective studies where a lot of their data is going to be pulled from large electronic databases. So what you would do is kind of like what I did in my example. You'd take a smaller random sample from the database, and from there the macro can automate the calculation of the effect size and suggested necessary sample size to meet the power and significance levels that you're looking for. And this will help you from unknowingly pulling too few data to reach significance or detect true effects in the circumstance that true effects exist. And it's also going to provide a valid sample size to aim for once you have done the calculation from your simple random sample. And that avoids expending way too much human labor, research time, and cost from pulling excessive data to reach some sort of gratuitous or overzealous sample size. So I think in that regard, this macro will be very beneficial for researchers doing retrospective studies. And here are the recommended readings. You can find all of them here. And thank you so much for checking out this presentation. It means a lot that you spent the time to review it. We are currently working on pushing this macro to our GitHub at Spectrum Health. But in the meantime, if you're interested in it and you want the code or you have any questions, feel free to reach out to me via email with either of the emails below. And thank you again for checking out this presentation. I hope you enjoyed watching it as much as I did making it.